So today we're going to talk about the n equals 4 Young's theory. Okay. Just to set the context, let us remember that prior to today's discussion, we discussed n equals 1 theories, and in particular this large class of n equals 1 theories, which is SUN theories coupled to 2NF chiral multiplets. We asked about the IR behavior of this theory. We found that the IR behavior was very different depending on how many chiral multiplets we had. Roughly speaking, when the number of chiral multiplets was small enough, the theory confined, sometimes in a way that prevented a vacuum from existing for this Affleck-Stein-Seiberg superpotential. But when you added masses, there was a nice vacuum and there was a confining theory. Then you went up in couplings, we got an infrared free theory. When NF was 3 by 2 NC up to 3 by 2, we got a theory that was conformal, very strongly coupled. The infrared theory was infrared 3, but in terms of some dual degrees of freedom. Okay. Then we got this theory that was conformally invariant, with very strong coupling at 3 by 2 NC, and then very weak coupling, and the coupling became weaker and weaker and weaker until it went to 0 at 3 NC. And then the theory was infrared free in terms of its usual degrees of freedom, the Lagrangian degrees of freedom at large. Okay, so the question, why did I bring this up now? I brought this up to say that the question that we had there was, what is the IR behavior? And we got a beautiful zoo of potential IR behaviors which we could characterize in great detail in these words, but not particularly quantitatively in terms of equations. For instance, when we looked at the when we were interested in if we were interested in the range 3 by 2 NC up to 3 NC, we know that there's this conformal field theory, and nowadays we can compute some things about this conformal field theory. We can compute its superconformal index. Maybe this is a calculation I'll go through at some point. Because you know the UV theory, and by arguing that the superconformal index renormalizes very little, even when you leave conformal invariance, you can compute the superconformal index. So you get some information about the theory. So on. But if you want to know what is the spectrum of operators in this theory, even the spectrum of all supersymmetric operators and so on, a bit hard to know. Okay. Then we looked. This was for the n equals 1 theories.
So you can calculate the index even after leaving the conformal?
Yes, you can calculate the index even after leaving the conformal. Even after. So this was something that was discovered after the discovery of the index in work by Seiberg. Well, you know, the history of the discovery of this, it's complicated, but Rommelsberger, this guy Rommelsberger, had this basic idea, though it was a bit, when you read his paper, it's a bit confusing why it works. And then Seiberg and friends, Seiberg and some students cleared this up completely. And the main point, maybe I'll go through this in it's a very interesting thing. The main point is that, you see, the superconformal algebra is this algebra SU2, 2/4. Or in this case SU2, 2/1, so n equals 1 theory. Okay, and that full algebra is not preserved along flows. However, you can arrange it so that the flows preserve a non-trivial subalgebra of this algebra. And the fact that this non-trivial subalgebra is preserved is enough to argue some things. Okay, it's interesting that if you take this theory on a sphere, and you add a mass term, it's possible to do it in a way that preserves a non-trivial subalgebra of this SU2, 2/1.
So even the supersymmetries are broken, or only the conformal algebra?
It's some mix of the two, because we're looking at it on a sphere. Okay, so when you look at it on a sphere, the when you think the supersymmetries and superconformals get sort of mixed up. Okay, so maybe at some point I will go through this calculation. It's actually very interesting. This reasoning, it's very interesting. This, by the way, maybe there's something even better now, but this, by the way, I feel is the most spectacular evidence for Seiberg duality. Because you can compute the index of the original theory, you can compute the index of the dual theory. And now, if Seiberg's duality is correct, these indices have to be the same. But they come from different UV theories. So the calculations are not the same. And you get two different mathematical functions, and then either using some identity that was known or extending some known identity, you can show that these are actually equal. So it's a highly quantitative check of Seiberg duality, this matching of indices. I will, maybe in the next lecture, maybe we can go through this. It's a very nice and a very beautiful story. Okay, that was the n equals 1. In the n equals 2 theory, we were in slightly better shape. A lot of when we were looking at small nf, a lot of our attention was focused on trying to find the potential, the superpotential for scalar fields. But n equals 2 supersymmetry immediately forbids superpotentials. Okay, so we had these scalar fields which were in the vector multiplet, and we just immediately knew that there were flat directions, leading to Higgsing of the theory. Okay, so we turned our attention not to the question of what, and along these flat directions, it was pretty clear what the theory was. It was some U1 theory, which at low energies was free. Okay, our attention was focused in trying to ask what is the precise effective action of this U1 theory as a function of where we are, and most crucially, are there places where this U1 effective action breaks down and something interesting happens? Where these massless monopoles and ions, right? Okay, that was the nature of the question we asked them. Okay, now we're turning to a theory that is even more supersymmetric. Okay, and by the way, we got the non-triviality of this function, this f, this A and A dual, this f of A, that we computed in the Seiberg-Witten solution, as you remember, was closely connected with the fact that the theory was not a conformal field theory. Right? For instance, when we went to A equals infinity, the monodromy around infinity was effectively a measure of the beta function of the theory. Okay? So we had a highly non-trivial function on this moduli space. Okay? Now in the case of the n equal, okay, so now we're going to turn to a theory that is even more supersymmetric, and when this theory was first studied, perhaps the reason to be interested in it was that it was the most it's one of these theories that's most supersymmetric theory possible. Now we've got many more reasons to be interested in it, especially because of ADS-CFT. Okay, so let me introduce you to the n equals 4 Yang-Mills theory for the next few minutes. Okay, let's take SUN. Let's take the SUN theory. Okay, so what are the fields of this theory? Well, the fields of this theory all lie in a single multiplet. Do you remember how that went? Do you remember our counting? This theory has 16 supercharges.
This is in 4 dimensions.
Yes, everything, yeah, this is in 4 dimensions. This theory has 16 supercharges. And we're looking for a massless multiplet in a theory with 16 supercharges. So if you remember how we made these supersymmetry multiplets, half of the supersymmetries were just inactive. For the massless case. Half of them squared to 0. What?
Q bars.
They were the things that P minus. Yeah,
You turn on only one.
exactly. Okay, so half of them squared to 0, so there are only 8 active guys. Then these 8 we divide into 4 creation, 4 annihilation. Okay, 4 and 4 annihilation. Okay, and we take these 4 creation for we take a vacuum state that is annihilated by all the annihilation operators, act on it with creation operators. Okay, now the difference between the vacuum, the difference in spin between the vacuum. Let's say that we choose that the vacuum is the guy that is annihilated by all operators which have spin minus half. So that means the vacuum is the lowest spin state. Okay, the creation operators all have spin plus half. Okay, so the difference between the spins of the vacuum and the spins of the highest spin state is clearly 4 into half, which is 2. If we want the minimum modulus of spins, which is the same as getting actually a CPT invariant spectrum here. We have to choose the spin of the vacuum to be minus 1. So the spins then range from minus 1 to plus 1. Okay, and the total number of states in this multiplet is 2 to the power 4, which is equal to 16, and they range from states that have spin minus 1 up to spin 1. Okay, we can count them a little more seriously. We can take the states with spin minus 1. So there's one state, and there's one state. So let's do spin and number of states. So minus 1, there's number of states is 1, it's a vacuum. Okay, then the states with spin minus half, that's 4, because you can act on the vacuum with 4 creation operators. The states with spin 0, that's 4 choose 2, because you can't act with the same thing twice because they're fermionic. Okay, so that's 6. Then the states with half is 4 again. It's 4 choose 3, which is same as 4 choose 1. So that's 4. And the states with 1, that's 1. Now we can look at the physics of this. This and this give you the two helicities of a massless gauge boson. Spin 1 or spin minus 1. That way or that way. These guys together give you 4 wild fermions. And these guys gives you 6 scalars. Is this clear? Okay. So the field content of the n equals 4 theory is A mu, then there's psi alpha, and I'll put an I here. This, yeah, let's put A here. A runs from 1 to 4. These are complex wild fermions. Okay, and then there are phi's, which are real scalar fields, and we have I. Okay, just to make sure we've got everything right, let's count degrees of freedom. Bosonic degrees of freedom here, counting one scalar degree of freedom as 1. There are 2 bosonic degrees of freedom, the massless gauge field. There are 6 bosonic degrees of freedom in 6 scalars. And here there are 8 complex fermions, but complex cancels with the fact that fermions are first order, and so there are 8 degrees of freedom in these fermions. So total number of degrees of freedom is 8 bosonic, 8 fermionic, making up the 16 degrees of freedom of the multiplet. Is this clear? Okay, so this is the field content of the theory. So far I have not referred to the gauge indices. But of course, A mu being a gauge field is in the adjoint. And then all of these are in the same multiplet. So under gauge symmetry, they all transform the same way. So all fields are in the adjoint. Okay? So every field here is an adjoint field.
The supersymmetry takes you from one field to the other.
Exactly.
Commutes with
And commutes with gauge transformations. Okay. Now, in this, let's look at these. These indices are very clear, right? This is a vector index in space-time. This is a spinor index in space-time. What about these indices? Okay. Something I have not told you, but I'm telling you now, is that n equals 4 Yang-Mills theory, that using the fact that it's n equals 4 supersymmetric, one can argue quite simply that this theory has to be conformally invariant. Okay, I'm not going to try to make this argument here for you.
You can say that there's no mass field. Coupling.
Well, the coupling constant in the classical action is always massless. The question is whether the beta function generates a mass scale. Okay, and there are various ways to make this argument. One of which is basically to argue that supersymmetry. One way to make the argument goes this way. What? There's no flavors. I mean, no. Oh, you mean one loop beta function, of course, vanishes. And if you use the fact that in n equals 2 or higher theories, one loop beta function is exact, you can do that argument. However, you may worry that there is a non-perturbative beta function, whatever that means. You cannot write a superpotential. But yeah, even more, you see, in n equals 2 theories, you cannot write a superpotential. And yet there is a non-trivial beta function. Okay? One style of argument goes this way. One can use supersymmetry to show that the metric on moduli space on Coulomb branch is flat. Now, do you remember that in the n equals 2 theory, the metric on moduli space, this is the thing we computed, right? The Seiberg curve. Its winding at infinity captured the beta function. The fact that this metric on moduli space is flat tells you that the metric on the moduli space of these scalar fields is independent of the coupling. So it tells you that the effective coupling constant of this theory is independent of the cutoff, and therefore that the beta function vanishes. This is one way to make the argument. There are many ways people have tried to make very clear non-perturbative arguments for the vanishing of the beta function. In perturbation theory, as Chintan said, it's obvious. You can just do a calculation and check. Okay? But I'm not going to give you a serious... of course, if there are requests, at any point I could go into any direction you guys want. If you're interested in understanding proofs for just tell me. Okay? But that's not the point of today's lecture. Okay, excellent. So this theory has 0 beta function. And it's conformally invariant. For all G, for all choices of coupling constant. Actually, this theory can be defined with a coupling and the theta parameter. So the coupling constant is complexified. So let's say for all tau, where tau as usual is 1 over g squared plus I theta, or maybe I over g squared plus theta, the usual thing. We'll write down the formula in a bit. Okay? So this is a striking thing about this theory, which was not there in any previous theory. Namely, that the theory defines a line, or more precisely a plane of fixed points. Okay? phenomenon that is extremely unusual in the renormalization group above 2 dimensions. In 2 dimensions, we see lines of fixed points all the time. For instance, a free boson with which is periodically identified, the radius of identification of the free boson gives you a line. Okay, so in 2 dimensions, it's not uncommon to see lines of fixed points. Or Calabi-Yau's target space, conformal field theory and world volume of Calabi-Yau, world volume of K3. So it's parameterized by the moduli of the Calabi-Yau, the K3. So a line or a sheet of fixed points. Okay, in higher dimensions, it's very unusual, and I don't know of any example outside supersymmetry where it happens. Okay, but so the structure of the renormalization group here is that there is this line, or more precisely, complex line. So it's a plane of fixed points. So you can have RG flows coming like this, and so on. There are different conformal field theories at different values of tau, and you can tune this thing. Very unlike, say, the Ising model, right? The Ising model at conformality is one theory. It's not got a tunable parameter. N equals 4 theory at the conformal point has this tunable parameter. Okay? So the infrared physics of this theory is unlike anything we've seen so far, because it has this complex line of fixed points. Okay? So it's one complex parameter set of conformal field theories. Okay, excellent. Now, okay, fine. Now, let me write down very roughly the action for this theory. Okay? The action for this theory is tau. I'm writing in components. There's, of course, trace f mu nu f mu nu. Then there are the kinetic terms for the various guys. So there's psi bar d slash psi plus d mu phi square. Oh, sorry, let me backtrack. I now remember the reason I started telling you that it was conformal. I wanted to explain these indices, right? Okay, I wanted to explain these indices. Now, let us remember, we've gone through all these lectures on conformal invariance with supersymmetry, namely superconformal invariance. Let us remember that in a theory that has 4 supercharges, in 4 dimensions, if it's superconformally invariant, then the algebra is SU 2,2/4. Okay, the 2,2 part gave you the SO 4,2, the conformal invariance, and the SU4 gave you an R symmetry. Notice that the number of supersymmetries was, remember that if the number of supersymmetries was anything other than 4, 3 or 2, then the R symmetry would have been U2 or U3. But exactly at 4, if you remember, there was this decoupling of one thing in the algebra. Okay, so this guy has, of course, the bosonic symmetries ISO 4,2, that's just conformal invariance. Fine. But there's also SU4. Now, it just happens to be true that at the level of Lie algebras, SU4 is the same as SO6. Okay, let's do the roughest check possible. Let's do counting. SU4 has 4 into 4 minus 1 generators, so 15 generators. Whereas SO6 has 6 into 5 by 2, which is 15 generators. Okay, and these two, the commutation relations of SU4 and SO6 just happen to be the same. The way it works is so it goes like this. We use this isomorphism, by the way, in arguing that the superconformal algebra existed at all, right? And the way it works is that the fundamental or antifund of SU4 maps to the chiral or antichiral spinor of SO6. Okay. On the other hand, the adjoint of SU4 maps to the adjoint of SO6, which is antisymmetric tensor, and so on. Okay, the 6 of SO6 is presumably it's presumably yeah, how does it go? Is it the self-dual? Let's see. And what is the 6 of SO6? I'm thinking it's probably 2-index antisymmetric, alpha, beta, and then self-dual. Let's see. It's 4 into. Yeah, what is it? Give me one. 6 of SO6. Is it? I'm trying to think whether it's the chiral times chiral or chiral times antichiral. Just meant plus. Sorry, let's work it out. So plus, and we need plus, minus, right, in order to get a 6. So I think it's chiral times chiral, but why not antichiral times antichiral? Oh, and sorry, minus plus, minus. Yeah, it doesn't quite work, right? Right. Okay. Yeah. It looks to me like chiral times antisymmetric of chiral spinor times chiral spinor is the 6. Do you agree with that? Let's check. If we make the antisymmetric of the chiral spinor with the chiral spinor, we need to choose a pair of chiral spinor guys which are not equal. Chiral spinor guys are plus, the 4 guys in the chiral spinor are plus, minus, plus, and minus, plus, minus. So let's take this pair, this guy with this guy. That will give 1, 0, 0. We'll get the vector, right? I think so too. Take this guy with this guy. Of course, we'll get the others. We'll get all the plus minus ones, right? Yeah, sounds right. So I think this is right. I think that the vector of SO6 is chiral times chiral of SU4.
SO6.
Of? Chiral times chiral of SU. Yeah, of SO6.
Fundamental times fundamental.
Right, exactly. So in the psi bar gamma mu psi, both are chiral basically. Yes?
What are these plus and minus?
These plus and minuses are the charges under the 3 kartans of SO6. Okay, so you take rotations in the 2 planes. Okay, fine. Okay, excellent. So, yeah, so this guy here, then, that psi A was a chiral spinor under SO6, or equivalently a fundamental under SU4. Whereas this phi I was a fundamental under SO6, or equivalently this antisymmetric of chiral spinors under SU4. Okay, so let's just work in SO6 language. So the gauge field is invariant under SO6. The fermions are a chiral spinor, and the bosons are a vector field under SO6. Is this clear? So this gives you an explanation for these numbers. They transform in some multiplets of the R symmetry. Okay, one last thing that we need is to okay, yeah, I mean, might as well. I should tell you about the supersymmetries of this theorem. Okay, so the supersymmetries of this theory transform in the supersymmetries of this theory transform in once again in a chiral spinner of SO6 and a spinner of spacetime, a wild spinner, and then there are the superconformal, which we're not talking about right now. Okay, very roughly, let's try to write down the supersymmetry transformations of all fields. I'm going through this kind of thing in more detail for the n equals 4 theory than we did for the other theories, because n equals 4 theory is special, right? So much of what we do in string theory, well, a fair fraction of what we do in string theory either uses the n equals 4 theory or is informed by knowing how it works. So maybe this theory we should understand a little more detail than this.
So what will we be using, SO6 or SU4?
It's up to you. They're completely the same. I often think in terms of SO6. Okay, but it's really up to you. Okay. Okay, so yeah. Actually, if we've chosen that psi up there to be a chiral spinner, then this will be an anti-chiral spinner. Okay, this will be the index that can contract with the chiral spinner. Okay, so let's just put some up-down notation. This up-down is most natural if we. So I put the psi up there. So let me put it down here. This up-down is most natural if you think in SU4. Fundamental, anti-fundamental. Okay, so let's see. Now, let's see how this guy transforms. What is the action of this Q on phi? Now, phi was a vector, but let's think of it as an antisymmetric of two of these spinner or SU4 fundamental indices. Let's call this Mn. Okay, so it's very clear just from matching of quantum numbers what we can get on the right hand side. You see, this guy was dimension 1, this guy is dimension half, so we should get something dimension 3/2. There's a spinner index, it should be a spinner, and something should happen with these colors. Okay, any guesses for what can appear on the right hand side? Psi itself, no derivative. What? Gamma mu. Yeah, okay, if you think in SO6, just let me write down and then you'll see. It's a gamma if you think in SO6 language. But no derivative, because d of psi would be dimension 5/2. Yeah, we want 3/2. Yeah. Psi n minus delta a n psi m. It's pretty clear, right? Nothing else could work.
So psi has the space-time index.
Psi has the space-time index. Yeah, phi and psi both have space-time indices. Space-time labels. Okay? Spin-time index, yeah, alpha. Yes. Right? Clearly you're acting a spinner on a scalar. You're going to get a spinner. It's got to be dimension 3/2. It's got to carry one SU4 index. What else could it be? Okay, let's do a few others. What about this guy? Any guesses for what it might be? First tell me, what should the dimension of the right hand side be?
1, 2.
And I've messed up indices. Psi a, let's call this alpha, let's call this beta. Dimension is 2, correct? Because half plus 3/2 is 2. Okay. Great. It is
Could be a vector under space-time.
yeah. It should be either a vector or a scalar under space-time. Yes, it should be either a scalar or a vector under space-time. But what? I can't hear you.
It has to be derivative, right? For this two of the that.
Yes, absolutely. There has to be a term because it is Q on the left. Very good. Very good, very good, very good, very good, very good. Very good. Yeah, just 1 minute. I'm getting confused about indices. Could be a delta AB F alpha beta. Yeah, right. This will go like delta AB F alpha beta. What?
What is F alpha beta?
F alpha beta. F alpha beta. Yeah. This is the self-dual part of, a field strength is F mu nu. Okay? But now let's look at it in SU2 times SU2 language. Okay? So this field strength is a 3 plus 3 in SU2 times SU2. It's a 6. It's 6. Field strength is antisymmetric of SO4. Antisymmetric of SO4, 6 components, 4 into 3 by 2. But let's look at what that antisymmetric of SO4 is under SU2 times SU2. Okay, remember antisymmetric of SO4 is the adjoint of SO4. So it's the adjoint of SU2 plus adjoint of SU2. Because adjoint is a fundamental thing in group theory. Okay, so it's a sum of two representations. Another way of saying it is that tensors, antisymmetric tensors of SO4 are not irreducible representations because you can put a duality or self-duality or anti-self-duality condition on them. Right? You can put the condition F mu nu is equal to half epsilon mu nu alpha beta F alpha beta. This plus minus, this cuts down the solutions, breaks it up into two irreducible representations. Okay, so the guy that is self-dual is the 1 of SU2 and 0 of the other SU2. Adjoint of SU2. And so that 1 of SU2 can be built by the symmetric combination of spins. So that's this F alpha beta. It's the self-dual part of the field strength. All good? What? Why not the derivative of scalars? That will come when you do Q with Q bar. These Q's are complex supercharges. If you remember, it's Q with Q bar that has derivative in it. That required alpha with alpha dot. Right? A derivative is alpha with beta dot. That can make a derivative. Okay? What?
Root over of derivative
A root over derivative. F has one derivative, but it's not. I think Diksha was asking, why aren't we seeing the supersymmetry algebra? Why aren't we seeing that Q is squaring to derivative? And therefore, when we act twice on the scalar, we get derivative of scalar. Why aren't we seeing that? And it is if we act with Q and Q bar. Let's see one of the relations with Q bar.
Q bar will be 1 or maybe dimension will be 1, right?
Will be 1, good. Therefore, that's the same dimension as a derivative.
Derivative of the scalar will be 2, right?
No, but Q with Q bar on scalar. Right, excellent.
Q with Q bar, according to sociology, is P, right? P is the derivative.
Yeah, exactly.
Exactly. Okay, let's see how that works. Okay. By the way, this field strength here will be the full field strength. It will be del mu a mu plus del mu a mu, but then also with the a mu commutator a mu. So just gauge invariance tells us that this has to be, fixes some nonlinearity in this supersymmetry transformation. Okay, let's look at the others. Let's look at some Q bars. Now Q bar lifts this index because it takes fundamental to anti-fundamental, and this becomes alpha dot. Let's look at this guy on phi first. Phi mn. Any suggestions for what this might be? Yeah. This guy could be epsilon a b a m n p psi bar p alpha dot. Right, because we're in SU4, so 3 fundamental indices is the same as 1 anti-fundamental index. Okay, and note how the dots are also working out nicely. Exactly, Kana. Okay, now what about Q bar A alpha dot on A alpha dot on psi. Equivalently, I could looked at Q on psi bar, but okay, let's look at Q on psi. Okay, this psi has a B and beta. Okay, so now we will get what Diksha wanted, which will be equal to D alpha dot beta phi AB. Okay. However, it's possible to get one more thing here. Actually not, right? This way because this. Yeah, no. It's possible to get one more thing here. Oh, is it in the other one? It's in the other one. It's in.
It should be a vector under space-time.
Vector under space-time. Yeah, there's nothing more you can do. This is just what it is. This is just what it is. Okay, I wanted to see. There's one more that I wanted to show you, and let me see what that is.
We can only have gauge invariant things on the.
Just one. We can only have gauge invariant. If you start with something gauge invariant, it will only be gauge invariant. Just one minute. I missed one term. What? No. Auxiliary fields not. Auxiliary field, we're working on shell. Auxiliary fields are not. But no, I want to see the phi commutator phi. There's a phi commutator phi on the right hand side somewhere. When you act with a supersymmetry on a fermion. I just want to see that. Give me 1 minute. Where is that? Yeah, I think here. Let's say phi. How are we going to get this? So just one second. Sorry. This how are we getting the R symmetry in this? Oh. Yeah. This guy can in addition have let's write this phi mn phi pq with an epsilon. So this guy becomes a b and this guy becomes epsilon mn p and a. This can also appear.
And is there epsilon alpha beta?
Epsilon alpha beta. In this is a two-dimensional spinner, right? SU2 spinner. So epsilon is a scalar.
Also, this is A, right?
What? A in epsilon. Oh, wonderful. So we've almost finished now. This guy, the Y with Q acting on psi bar is basically the same as this. Okay, take some stuff. So that I'm not writing. Let's also write Q acting on, let's also get just roughly Q A alpha acting on F beta gamma. I've not written commutator on the other side. Okay. If we write Q on F, now the right hand side has to be of dimension 5 by 2. Okay. Right hand side has to be of dimension 5 by 2. And the only and has to have, so now this F can have many kinds of indices. It can have two SU2 indices, one SU2 left, one right, and two SU2 right indices. So we have to get them all straight. Okay, this guy will just be 0 because there's nothing we can write. There are too many SU2 indices. Right, because the only thing we can do is it's got to be of dimension 5 halves. A derivative of a psi would do it, except a derivative always has at least one dotted index. Right? So this is not going to work. If we do Q A alpha on F beta gamma dot, okay, F beta gamma dot, and now A is, we're getting confused because A is down here. Now we do this, we could have an d alpha gamma dot of even this looks like 0, right? Can you think of anything this could be? We want a derivative of a psi bar, because psi bar has lower A indices. Of the we want a derivative of the psi bar, this guy, but that has a dot. So this is also not going to work, right? This will also be 0. And then some of these are 0 when you think about it from equations of motion, because the fact that del anyway, and finally you look at Q A alpha F beta dot gamma dot. Okay, this will finally work, because this we could have as d alpha gamma dot psi bar. Okay, are we calling psi bar? Yeah, psi bar A beta dot plus the other term, plus the exchange term. It will be plus here because these were symmetric. What? F F is antisymmetric if thought of in terms of mu indices. But when you think of it in terms of SU2 indices, it's a vector made out of two spinors. Right? So this will be plus the other term. Okay, we could go on. We have not listed all the supersymmetry transformations, but you get the point, right? What I wanted to show you is that just charge balance is so constraining that it almost completely fixes the supersymmetry transformations. Okay, that it almost completely fixes the supersymmetry transformations. And in fact, if you now demand closure of the algebra, you will find that it completely fixes it. Just completely fixes it with with a constant here, for instance, completely determined. No ambiguity left. Okay, fine. We're going to use the supersymmetry algebra when we look at the a little bit when we look at zero modes of monopoles. But quite apart from that, I thought I would just once show it to you. It's very simple structure, and you don't need to remember anything. I didn't remember anything coming to this lecture.
Closure means acting again with another Q.
Sorry, say again?
Closure means acting again with one more Q.
Well, I just wanted to check that the supersymmetry algebra was obeyed. Okay, so that Q with Q is whatever it should be, and Q with Q bar is whatever it should be. Okay, and demanding that fixes everything. Actually, you can also demand the Jacobi identities, the super Jacobi identities. But we got the supersymmetry algebra by demanding that. Okay, so now if we just demand the supersymmetry algebras is obeyed, it fixes completely everything, and it's extremely rigid. There's nothing else you can add or subtract. There's no superpotential you could have added. There's no kinetic term you could have changed. Okay, at least if you demand that it's two derivative, there's nothing you can change.
Is this because of n equals that maximum?
Because n equals 4 supersymmetry, so it's so rigid.
So if you use less supersymmetry, then you have to.
So if you use less supersymmetry, let's say when we use n equals 1 supersymmetry, we know what the right hand side was, but in terms of the auxiliary multiplet,
right.
And the auxiliary multiplet was determined in terms of the superpotential. If you just did it in components, you would find an ambiguity, because you could have added any superpotential.
Why don't you have central charge terms on that?
Why don't we have central charge? Because we're working with the conformal theory. We're not allowing any terms with a mass scale in them. Okay? In the conformal theory, there's no central charge. Okay? You will have central charges if you go off on Coulomb branch. Then where you are on Coulomb branch will become a mass scale that can support a central charge. Okay, right now we're just at the conformal fixed point. Okay, excellent. Fine. Fine. Any other questions about this? As I was saying, in the n equals 2 theory, you could, at two derivative level, change the theory by changing the prepotential. Okay, that if you try to work out in component language, would be an ambiguity in the algebra. The n equals 4 theory, there's no ambiguity. It's just completely fixed. Okay, now closure of the algebra also requires the equations of motion. This algebra will be closed, will give you the right algebra on shell once you impose the equations of motion on the right hand side. This you remember, right? When we studied even the n equals 1 theory, if we worked with auxiliary fields, the algebra closed without any equations of motion. But we eliminated the auxiliary fields, the algebra closed only once we imposed the equations of motion. Okay? Here we are doing no auxiliary fields, so we should expect closure only up to equations of motion. But the equations of motion that are required to get this algebra to close are the full nonlinear equations of n equals 4 Young's theorem. Okay? Since the equations of motion appear on the right hand side, the algebra only closes subject to these equations of motion. The Lagrangian is also determined completely unambiguously, because the Lagrangian from which these equations of motion can be derived.
Just from supersymmetry, you can define the whole.
Supersymmetry and demanding two derivative.
Two derivatives, yeah.
Just from supersymmetry and demanding two derivative, and the two derivative comes in saying that there's no dimension full scale in the problem. Right? So if you take the theory with no dimension full scale, then nothing. Right? Just from supersymmetry, you fix everything. Okay? It's an extremely powerful powerfully constrained system, and it stems from the fact that it was maximally supersymmetric.
How do you get the equations of motion?
How do you get the equations of motion? You see, what you're going to get, for instance, you've got this term here. Okay? Now, when you work out, I can't remember which, but one of the Q commutators, you will get what you expect plus a term that looks something like, let's say I work it out on, I work out a Q commutator on del mu or phi. Okay? Oh, you will, or something, you get what you expect, but plus an additional term which looks like this, with an extra phi maybe, stemming from those guys here. Okay? And the algebra will work out provided this thing is 0. So that is the equation of motion you need to impose. Do you understand? It's important here that we fixed the right hand side, including on nonlinear terms. For practice, you could first work this out linearly. And then you will, in order for this whole thing to close, it will be required that del square phi is 0. That's an equation of motion. But once you include the nonlinear terms, you will get additional nonlinearities which come from the potential in the Lagrange. Is this clear? Okay? So the whole thing is completely tightly fixed by supersymmetry, and indeed this is another way of arguing arguing in some sense that the beta function had to vanish because well, at least on Coulomb. Yeah, fine. This is the same argument I gave you before. Really. Okay, excellent. So now we've got some familiarity with this theory. What does the Lagrangian of this theory look like? The Lagrangian of this theory looks sort of like this.
You are saying since the equation of motion is so fixed that you can't change the Lagrange.
Exactly. Fine. So now let's look at the Lagrangian of the theory. So the action has, of course, f mu nu, f mu nu. It has d mu phi ab, the whole thing square, mod square, plus d mu psi bar, d mu psi. Okay? And then it has two other kinds of terms. The first other kind of term is a potential term, which takes the form phi. I'm writing this as I, okay, so that I is AB. Phi I commutator phi j, the whole thing squared, sum over all pairs ij. Okay? And the second term is a sort of psi commutator phi phi. Now, it's a Yukawa type term. Now I have to get the indices. What am I saying? It's phi commutators, I say. Okay? It's this kind of term, a Yukawa type term, and I have to get the indices working. So the indices of this thing here, so we want phi AB, let's say, and we could have a term here which was phi C. There will be one term which is phi C, phi D, alpha, beta, epsilon, A, B, C, D, and another term which is phi A, B, psi bar, A, alpha, dot, psi bar, B, beta dot, B, epsilon, alpha dot, beta dot. Okay? Yeah, these indices here will be edge, and just 1 minute, let me get the phi indices right. The indices on the potential term, that's basically, how does that go? Just 1 minute. Yeah, that's fine because it's just mod squared. This is like vector indices can be raised and lowered at will. So it's just that. Okay. So the Lagrangian of the n equals 4 theory, there's an overall coupling constant outside this thing, and then the Lagrangian looks like this. Okay. Fine. That's all I wanted to say about what the n equals 4 theory was, what its Lagrangian looks like, and of course the fact that it's conformally invariant. Any questions or comments?
Is there any review or any lecture of that?
These indices and so on?
Yeah, also the beta function.
Beta function, there are papers by Seiberg where he establishes the non-perturbative zero of the beta function. I could review them next class if you were interested. I'll do that. Okay. There may be reviews, but often it's better just go to the paper. Okay.
Also the perturbative calculation, they in their papers or
Perturbative calculation of the beta function? Oh, that's very easy. Yeah. It will be in the paper. But yeah, that's very easy. That's just using the formula, right? It's a one loop calculation. Okay. Okay, excellent. Now that we have this basic picture of the n equals 4 theory, you might ask, what is it that we want to know about this theory? Okay. I've already told you that the motion that if we try to do what we did for the n equals 2 theory, namely study this theory as a function of where you are in moduli space, the answer to that question is extremely boring. It's true, let's say you take the SU2 n equals 4 theory. It's true that once again that the low energy theory is a U1 theory. The coupling constant of that U1 theory is just same as the UV coupling that you put into the n equals 4 theory. The metric on moduli space of this U1 theory is flat. At two derivative level, there's really nothing to compute. Now you can, and in fact it's possible to compute higher derivative corrections to this U1 effective action, but it's a bit stretched, right? Why do you want to know that? Okay, in fact Seiberg has written a paper on computing these high derivative corrections, but okay, that's not really very exciting. Okay, so looks like we're done, right? We've understood the low energy behavior. It's a conformal field theory. Yeah.
High derivative thing.
What?
Why? What did you say about the high derivative?
Okay, suppose you take the SU2 theory and separate the two, turn on a wave for these fields. Separate the branes. Let's take a minute to understand the language separate the branes. As you know, n equals 4 Yang-Mills theory is the theory that appears on the world volume of D3 branes. The fact that we had 6 scalar fields is the fact that D3 branes live in 9 spatial dimensions, and therefore are codimension 6. Therefore, can be separated in 6 different directions, and these 6 different spatial separations are these phi fields. Okay? Gauge fields, of course, are the usual gauge fields, and then there are the fermions. Now, phi fields at the conformal point are just local fluctuations of the brane wiggling in these extra directions. But because the potential of this theory involves only commutators, and this is exact, remember, the potential of this theory involves only commutators, one has vacua provided for any values of these scalar fields, these phi's, provided they all commute with each other. Okay? Therefore, any diagonal values, if a bunch of 6 scalar fields all commute, by SUN rotations they can all be made diagonal. So any diagonal values of these 6 scalar fields represent a potential vacua of this theory. Okay? In terms of D3 brane language, the diagonal entries are the locations of these D3 branes in the 6 transverse directions. Imagine that these three branes live in 0, 1, 2, 3. They have some locations in 4 to 9. And the values of these locations are these diagonal entries. Okay? Let's take, for instance, the SU2 theory. The U1 part of U2 theory is just overall location of the branes. So let's say the center of mass of branes is at 0. So we are effectively now in the SU2 theory. The separation of these branes, the difference between eigenvalues is now the separation between the branes. It's the separation between the branes in the six different locations. Okay? So these vacua of the n equals 4 theory are the same question as what is happening in the branes when you separate them, when they're not banged together. The branes could have any locations in the transverse space as long as you don't change the fact they're parallel, they preserve the same supersymmetry. Okay? And the locations of all of the n branes are the eigenvalues here. They can have different locations in different dimensions. This is clear, right? So about the higher derivatives, what I said was this. Now we can let's take the SU2 theory and we can separate the branes. Let's say along the direction x1. Doesn't matter because of the SO6 symmetry, all directions are the same. So all that matters is the extent to which we have separated the branes. Now you could ask, what is the low energy effective action? Exactly as in our discussion of the n equals 2 theory, low energy effective action is U1. Okay? Because SU2 theory has been Higgsed down to U1. Because you've turned down a vacuum expectation value for an adjoint of SU2, which is a vector of SO3, which Higgses it down to U1. So once again we've got an U1 effective action. You could ask, what is the metric on moduli space for that? But that has a trivial answer. It's flat metric. Effective coupling is constant. The tau that we spent so much time computing, d by dA, which was a non-trivial function of where you are in moduli space for the n equals 2 theory, is just constant. Constant equal to the uv value of tau, because there's no running, no beta function. In fact, this is one of the arguments that there's no beta function. Okay? So now, is there anything interesting to compute at all on this? Well, what you can try to do is to calculate four f terms, f to the 4 terms. These are high derivative terms. These high derivative terms are impossible in the conformal theory, because an f to the 4 term is dimension 8. There needs to be a length scale to make up that extra dimension. However, here we have a length scale, which is the wave of the vacuum, the extent by which the planes are separated. So these f to the 8 term can come separated by vacuum separation to the 4, scalar wave to the power of 5 to the 4, and then with some structure and with a number. Turns out to be possible to compute that. So one loop calculation gives it exactly. But as I said, it doesn't seem very, unless you have a particular reason. Now there is an infinite number of things to compute, but we've got the basic idea of the physics quite clearly. Okay?
Why 4, why not 3?
Why 4, why not 3? Firstly, supersymmetry tells you that the first correction here is an 8, dimension 8 thing. It may be hard in general to produce. Okay. Yeah, maybe you could. You will want some f to the 3 term. You'd have to put the indices right. Perhaps it's possible without supersymmetry, I would have to think. But certainly with supersymmetry, you can just show that the first correction is of order n to the 4.
So the indices will be matched up.
What? Sorry?
So the indices will be matched up properly.
It will be matched up properly with the f to the 4 term. Yeah. Okay. Other questions? There was some discussion? Okay, excellent. So now the question is, what do we want to know about this theory? Well, we'd like to know a lot about this theory, right? I mean, we'd like to know scaling dimensions of all operators, we'd like to know all OPE coefficients and so on. But at the moment, we're not in this very sophisticated phase. We want general structural properties about this theory. What do we want to know about it? Now, there is a remarkable structural property about this theory, which is that this theory enjoys invariance under S duality. Okay? But this theory okay, so let me write down exactly what tau is. Okay, tau is the same thing, it always is. If yeah, please. I by g squared plus theta. Okay. Some 2 pi somewhere, theta by 2 pi. Because tau goes to tau plus 1. Yeah. Okay. So, claim. Okay. This theory enjoys invariance under S duality, which is that the theory at tau and tau prime is equal to A tau plus B over C tau plus D. These two theories give the same physics. Okay? There is some small issue about whether we're talking about S. If we're talking about the SUN theory, the SUN theory on one side maps to the SUN mod Zn theory on the other side.
That is SL2Z.
As that is, oh yes, sorry. A, B, C, D are all integers such that unit determined. SL2Z. All integers. Okay? We probably won't encounter the subtlety in what we're talking about SUN and SUN mod Zn. In any case, in the UN theories, they just map to each other. The UN theory on one side just maps to the UN theory. Okay, this is the claim. Okay, so this lecture and probably the next is largely to introduce you to this claim and to give you the evidence for it. Okay, now this claim here, notice that if you set theta, this, and we look at the theta equals 0, and we look at the part of SL2Z that keeps theta equals 0. Okay, that basically is tau going to minus 1 by tau. Okay, something that's imaginary stays imaginary, and you can get tau goes to minus 1 by tau by choosing A, B, C, D to be equal to 0, 1, minus 1, 0. Okay, so tau goes to minus 1 by tau. Ignore, suppressing theta for the moment, fixing on theories with theta equals 0. Tau goes to 1 by tau is this, tells you that g squared goes to 1 by g squared. So part of the statement of this SL2Z duality is that the theory at very weak coupling is same as the theory at very strong coupling. Okay? So historically, the idea that something like this might be true came about in a paper by Olive Monton, maybe somebody else. Okay? And before going into the more detailed evidence that we have for this theory, let me first tell you about their paper and what they thought about it. So what Olive Montonen and friends were doing was to study the SU2 theory. Okay, well they weren't interested, or maybe didn't know much about supersymmetry. They looked at the SU2 theory of Yang-Mills with an adjoint scalar field. And they just put by hand the potential for the scalar field is equal to 0. Okay? Then what they did was to look for the spectrum of interesting protected sort of particles in this theory. Okay, because they looked at SU2 with a scalar field with no potential, they realized that there was this Coulomb branch where you could separate set this adjoint field to be whatever you want. Okay. Once you did that, the gauge group, as we've been talking about, was broken from SU2 to U1, and there were the Higgs phenomenon happened, and you got W bosons, and the W bosons had mass. The mass of the W bosons was given by E times V, where E was the coupling. We've called it G. G times V, where G was the coupling of the theory. This is the usual Higgs mechanism story, right? It's just the fact that the minimal coupling comes with, G squared, A squared, V squared, phi squared.
What is V?
V is the vacuum expectation value of the scalar field. Okay, but then being smart people, these guys realized that there was another interesting excitation in this theory when we were on Coulomb branch, and this is the Topf-Polyakov monopole. You remember this monopole? We've talked about it before. It's a configuration in which at infinity the scalar field has modulus V, but it winds such that the direction in space is equal to the direction in SU2 space. And so there's a hedgehog kind of winding configuration. Okay? And you remember we discussed before that such a configuration, if it was pure scalar, would be infinite energy. Right? Because the angle is varying, you have something varying like angle, therefore derivatives are like 1 by r, therefore derivative squares are like 1 by r squared, but we're integrating over a 3-dimensional space, so you get r squared by r squared dr, so you get infinity. Right? Such a configuration would be forbidden in a theory of pure scalars, it would be infinite energy. Okay? However, if you in addition turn on the gauge field to make in such a way so that A mu precisely cancels that rotation, to make the covariant derivative 0. Okay, if you do that, if you precisely accomplish that, then this 1 over r squared becomes like 1 over r to the 4, and you get nice finite energy. But this configuration now has both winding scalars as well as a non-trivial gauge field. The non-trivial gauge field has 1 unit of magnetic flux. In particular, F mu nu A phi A, where phi A is this winding guy, integrated over an S2 is equal to 1 in the right unit. 2 pi probably. This is this magnetic monopole. Okay? This magnetic monopole was written down by Toft and Polyakov and worked out in more detail by Sommerfeld and Prasad. There is. Okay? Great thing about this monopole is that its mass is very easy to compute exactly. Actually, much easier to compute than to find the exact solution of this monopole. Okay? We can understand this from modern supersymmetry language. Its mass is given by a BPS bound. Okay? And when you compute the mass, you find that it is V, once again because there's mass scale by G. Actually, yeah. Let's deal with mass squares. It's interesting. Yeah. Am I talking about mass or mass square? Just a minute. Is G square M square is equal to this. M square is G square V square, right? And strange. Yeah, give me a minute. Just one sec, please. What is E square? Mass is G. Monopole mass, they say, is 1 by, I say it must be somehow in the G. I say, sorry. The monopole mass is 1 by G. This is sort of strange. Okay, I'll tell you why it happens. Yeah, it's because the action is in this statement. The action is being written as f mu nu plus d mu v, the whole thing squared, where d mu v is del mu v plus g a mu.
Is the mass computed from this action the same as?
You're wondering why it's not 1 by g square, right?
I have basic question like.
Yeah.
Just from classical action.
Yeah. Just classical action. Just classical action. That's the mass. The energy of that solution. The energy of that solution is the mass. Yeah. I have to say I'm wondering why it's not 1 by g square. And the reason is that this V, see, there would be a way of writing this. It's in this normalization of what we call V. There would be a way of writing. If none of you have this confusion, we'll move on. But do you understand? My confusion is this, that when we write the action as 1 by g squared times some stuff, then any classical solution will be order 1 by g square. Okay? But remember that this is, so why isn't it 1 by g square? But there's also this V. So two different field redefinitions of V will give you two different values of g square. So you have to be in the frame that where phi will map to phi under duality. That's when you can compare. Okay, so anyway, with the appropriate definition of V, this is how it goes. Okay, so the mass here was like was G. So on one side for the W boson, the mass was GV, and for the soliton, the mass was V divided by G. Okay, and so then Olive and Montonen looked at this and they made an extremely bold conjecture. They said, we conjecture that the theory of SU2 with a single adjoint scalar field is at coupling constant G is the same as SU2 with a single adjoint coupling field at coupling constant 1 by G. And under this duality, okay, from the mass, okay, under this duality, so you see, making conjectures based on very little evidence has a long history. Okay, and under this duality, the soliton will get interchanged with the W boson.
What is the evidence in that soliton and W boson have to have some similar properties?
Yeah, it's an excellent question. They just sort of noticed this. They had one or two other reasons, but it was basically this. Now, Kano, you're in very good company because this proposal intensely irritated a certain prominent physicist whose name starts with W, Witten, and he wrote a follow-up paper on it saying this is total bullshit. Okay, and he had very excellent arguments to back up his claim. First was the soliton was a scalar, whereas the W bosons were vectors. Okay, how can they map to each other? Second thing, he said, the soliton's existence depend, and this whole story depends on this flat potential. But the flat potential is a classical accident. You do a Coleman-Weinberg computation in this potential, you get a Coleman-Weinberg potential, it's not zero, so there's no flat potential anymore, so what are we talking about? The evidence has gone away quantum mechanically. Okay, a third objection that was made by him and others was, what does G goes to 1 by G even mean? Because in this theory with the adjoint superpotential, coupling constant runs with scale. So at what scale is G goes to 1? What scale does G goes to 1 by G? Okay, So, and there were other, we don't need to go through them all, but there were other objections. The proposal seemed justifiably, this was in the 1970s, okay, late 1970s. Justifiably, this proposal seemed buried within dishonorable funeral. Okay. Okay. Now, but it often happens in the history of ideas that an idea is wrong, but if it's interesting, it resurfaces somewhere else. Okay. For instance, the idea that quantum field theory was best described through analyticity of S matrices that are so prominent in the 1960s. Just was not the good way to think of QCD, but it's resurfaced today in all these studies of dispersion relations. It also gave rise to string theory. See, ideas can sometimes be wrong, but being wrong is not. Being wrong in your context doesn't mean it's not useful. Okay. So, it's this duality of Montonen and Olive that has resurfaced in the context of the n=4 theory. Okay? And this is now what I want to describe to you a little bit in more detail, and also to describe a little bit in more detail. And also to give you the non-trivial evidence for it. Let's take these objections one by one. The last objection was that the coupling constant runs in this theory with the single scalar field. So at what value of scale is G goes to 1 by J? Now, n=4 theory is a theory where the coupling constant doesn't run. So this objection is just not there. Okay. Then there was this objection that on one side we had a vector boson, and the other side we had a scalar. But look, as you know, now we're dealing with the supersymmetric theory. In supersymmetry, all states come in multiplets. So you may take a particular member of that multiplet and look at it, as we do for the W boson. But it's going to come in a multiplet. Both the W boson and the soliton come in BPS multiplets. Okay? And it's not difficult to argue that, it's the same BPS kind of multiplet. Okay? So both the W boson and the soliton have the same kind of fields, all of them. They're all in, so to say, a multiplet with a vector, scalars, and fermions. I'll describe this to you in a little bit when we discuss the zero modes of solitons. This will come in. I'll put some detail onto this. Okay? The point here was is to understand that this objection has also gone away. Okay? This objection has also gone away. And there were other objections people made to this proposal of Montonen and Olive, all of which you can very easily see just don't have water in the context of the n=4 theory. So given all of this, it's natural to wonder, is this old conjecture, which was certainly not true in the context where they made it, is this old conjecture true in the context of the n=4 theory? And various people made this suggestion quite early on. However, making a suggestion and finding evidence for it are two separate things. Okay? And the atmosphere in the 90s was not like it is today. Nowadays, if somebody proposes a duality and after 2 hours of examination you can't find a counterexample, we all believe it's true. But it was very different atmosphere then, where the burden of proof was on the person proposing the duality. Okay? So how do you find evidence? How do you find evidence for this duality? Okay, so that is the question that that Ashok posed himself. Okay? And the first observation that I think this was Ashok made was that this G squared goes to 1 over G squared, or G goes to 1 over G duality, is enhanced, is upgraded to a full SL, is necessarily upgraded to a full SL2Z duality. The reason for this is very obvious, it's just the Witten effect. So the theories that tau goes to tau plus 1 are definitely the same theories, because it's just theta goes to theta plus 2 pi. We also know that when we do that, the quantum numbers of all states will change. Okay? So the idea that, I hope I'm correctly attributing this, but I think it's Ashok, had, was that, look, if G square goes to 1 over G square duality is correct in these theories, then they must enjoy invariance under a larger group of dualities, this SL2Z dualities. Okay. Now, also because of the Witten effect, we know how the charges of these dualities transform under duality. We know that if we've got a state with NE units of electric charge and NM units of magnetic charge, okay, we've got a state with NE units of electric charge and NM units of magnetic charge, okay, then if we act with A, B, C, D on this, that gives us the quantum numbers of the state after the duality. Now, Ashok realized the following. Ashok realized that this allows you to make predictions for the spectrum of particles in any one theory. Okay? Because if we assume that there are no walls of marginal stability, and there are none because there's no, the analog of AD by A by AD becoming real does not exist here because there's no A and AD. You know, it's just the supersymmetry transformations are so simple, the formula for the central charge is so simple that these walls of marginal stability that could occur in the n equals 2 theory never occur. Okay? So that if at any value of the coupling some particle is stable, that must be true at all values of the coupling. Okay? So his idea was this: look, we know that there exist monopoles in these theories. We also know that there exist unit charge W bosons in these theories. And then the third thing he observed was that we know that there exist dions in these theories. This I'm going to tell you about. Okay, I'm going to tell you how we know this. This when we get to the quantitative part of. Okay, I'm taking a lot of time, I'm sorry, but when we get to the quantitative part of these lectures, I will tell you about that in detail. We also know that there exist dions in these theories of charge, 1 unit of magnetic charge and any number of units of electric charge. I will explain how we know this. We know this from semi-classical methods. Okay, all this we know. Now, but if it's also true that SL2Z duality is correct, then all the states that we can obtain by acting on the spectrum that we do know, okay, all the states that we can obtain by acting on the spectrum of particles that we do know, with the SL2Z transforms, that generates new kinds of states. Since we believe that there are no walls of marginal stability, these new kinds of states must exist at all values of the coupling. Okay? And so we get a predicted spectrum for n equals 4 theory on its Coulomb branch, spectrum of BPS particles, for n equals 4 theory on its Coulomb branch at every value of the coupling. Okay. Great, so that's a prediction, but how do you test it?
But what if I just how much was centered?
What if they, we'll check. You're saying what if there's no SL2Z transform that generates something new? But there are, right? Because we can just check. We know this, we know the charges, we know we'll do ABCD, we'll check. It's not true. Okay? One of the new particles that this thing turns out to imply, as again I'll show you in detail, is a particle of magnetic charge 2 and electric charge 1, and I believe also electric charge k for all odd k.
These are both magnetic and electric.
But these are things with magnetic charge 2.
Dions are required.
Well, no, these are dions, as you say. But the thing that people have previously studied that is easy to study is dions of magnetic charge 1 and any value of the electric charge. Okay, those are very easy to study by semi-classical techniques. Such dions, as I will show you, come about from just quantizing the moduli space of the single monopole. The quantization of that moduli space, you see the way it's going to go. We'll see this in detail. Maybe I should just start doing that. But anyway, this is just to orient you in this part. Please go on.
For any winding of the monopole, you get just one magnetic charge. So you wound it once.
Okay, no, but you see the configurations where you wind twice can be continuously deformed to two one-winding configurations. So that is interpreted as two monopoles. Okay? So, but let's look at the configurations where you have one winding. Okay? Let's look at those configurations. Again, we're going to study all this quantitatively, but just for orientation at the moment. Let's look at those configurations, the configurations where we have one winding. Okay? You write down a solution, it's somewhere in space. So, you can change its location as a function of time. That gives you a light mode, because it could have been anywhere in space. So, if you change its location as a function of time slowly, you get slow variation in action. Quantizing that mode gives you the states which have where the monopole have momentum. Clearly. So you get new solutions where the monopole is boosted. Okay? There's a more interesting new kind of solution. That new kind of solution goes this way. Remember that this monopole is characterized by the scalar field pointing in gauge space in the, identifying gauge space and rotation space. Okay? Now, suppose you do the following. Suppose you make a gauge transformation, a time-dependent gauge transformation, okay, in the same direction, in this direction that tracks where you are. Okay? If you make a time-dependent gauge transformation, which is almost a time-dependent gauge transformation in this direction, okay, this guy is pointing in this gauge space in some direction. But now you make it move in this gauge space as a function of time. So you make it execute a motion that would have been pure gauge had it been constant. But now it's become a function of time, so it's not quite pure gauge. Okay? This gauge parameter is a circle. So just like motion of the monopole in space generates solutions where it has some momentum in space, motion of monopole in this u1 direction, okay, this u1 circle direction will generate a configuration in which this monopole has momentum in this u1 direction, but momentum in that u1 direction is charge.
Oh, sorry, momentum for at a particular point, since the scalar field is pointing somewhere, you have u1. If you are talking about that.
Exactly. The u1 that is preserved.
u1.
Okay, so we've got a u1 preserved, and your gauge field is in some direction in this u1 space, in the sense that you can make a gauge transformation and gauge transform that gauge field. Now if you do that gauge transformation and make it a function of time, but not turn A0 on, so it's not quite a gauge transformation. You see, normally when you make a gauge transformation, you do a gauge transformation and make it a function of time, you turn A0 on as well. That is a gauge transformation. Now what we're going to do is to make a gauge transformation, but make it time dependent and set A0 to 0. This is not quite a gauge transformation, new physical configuration. Okay, but it's a physical configuration that involves some momentum in this gauge direction. Okay, and as you can imagine, and as we will see, it's a configuration which turns on an electric field.
Why is A0 central?
Well, you want let's say that we're working in the gauge A0 equals 0, for instance.
Staying in the gauge.
We just stay in that gauge. Right? All we do is, in that gauge, we don't want to deal with modes that are really pure gauge. All we do is, in that gauge, we notice that there were these gauge degrees of freedom that, if you make a gauge transformation by some, that move where you are, okay? And then we make that time dependent without turning A0 on to make it a physical thing to do.
If it were constant, it would have been a residual gauge.
It would have been a residual gauge transformation and therefore not appear in the action. Now it's not constant. So it appears but only very slowly. Because had it been constant, it doesn't appear in the action. So like a zero mode. Okay? And this maneuver will very easily in the single monopole moduli, moduli space very easily will allow us to show that there exist these Dion type solutions, new solutions that basically quantizing the zero mode motion around the single monopole solution, which is very well understood, gives us Dions of any electric charge. Momentum in this gauge direction will be the electric field, the electric charge. We'll see all this in detail. I'm just orienting you at the moment. Hi Shantani. I'm teaching a class. Can I call you in half an hour? Yeah. Okay, bye.
Electric charge will be the momentum in this.
Momentum in this direction, because it's a circle, that momentum is quantized. And so it's 1, 2, 3, 4. Okay?
These are the dions with any electrical charge.
Any electric charge, but one unit of magnetic charge. Now we get to the question. Of okay, all this was well known. Now Ashok, as in a way that I will show you, explained that if all this is true and S duality is true, then there must be states, Dions, with 2 units of magnetic charge and every odd unit of electric charge. I will explain how that comes. It's a simple thing. Okay. Now then he went about trying to test this prediction. Okay. The thing that makes this difficult is the following. 2 monopole moduli space is a complicated object. Okay. It is the quantum mechanics of 2 objects moving around.
Is it the top nut?
Yes. Yes. On the top nut metric. We'll discuss this. So it's the quantum mechanics of 2 objects moving around. Okay? And just as we could obtain the Dions by some property of knowing classical behavior in a single monopole moduli space. We could obtain all Dions of magnetic charge 1. Ashok's idea was we should be able to obtain the properties of all Dions with magnetic charge 2 by studying some property of the motion of 2 monopoles. In particular, he demonstrated that the existence of a 2,1 supersymmetric bound state was equivalent to the condition that there exists a certain kind of form on the metric of the 2 monopole moduli space. This is very similar to what we've discussed in the beginning of our course. Do you remember we discussed that supersymmetric states in some contexts were, in the simplest context, were harmonic forms. Okay, and when we put more supersymmetry, there was a little more structure in that space. You remember the idea, right? We got these forms by these quantizing these fermion directions and so on. that the wave function's dependence on fermions translated into wave function dependence on the forms. So Ashok translated, used previous work to translate the question of whether this two monopole, one dion bound state, supersymmetric bound state existed or not, into a question of the existence of a certain kind of harmonic form. We will discuss that. Okay, which is normalizable, and then he just by explicit construction found it. Okay, in later work people have shown that this is that his construction generalizes also that the number of these forms is exactly the number that is predicted by supersymmetry. Okay, so Ashok's evidence for this duality went like this. If we assume the duality, we get a prediction about the spectrum of the theory. But in the semi-classical regime, the prediction of spectrum a prediction of spectrum involving dions turns into a concrete prediction for the existence of some form on the moduli space of dions. The two monopole moduli space was not trivial like the one monopole moduli space, and yet simple enough that you could do explicit calculations. And he just explicitly found this form, demonstrating the existence of this bound state, this dion. Okay, this psychologically proved extremely important. Okay, I know it had great effect, in particular on Witten, who was very skeptical of S duality until Ashok's work, and then after a phase transition became a champion of S duality. Okay, and had a great impact on the community. Okay, so this is what I'm going to tell you about quantitatively. I'm sorry I've gone so slow in this class. Somehow the time has disappeared. Next class is when we will do the actual work. Okay.
But have people like constructed the predictions from like a 3-charge monopole or
multi-monopoles? I'm not sure actually. I don't know. My guess would be that maybe people have argued that they exist. These higher monopole things are extremely complicated. So to explicitly construct them may be out of reach. I'm not sure. You should ask Ashok next time.
So acting with this SL2Z, you will get only those.
You'll get a whole set of states. Okay? And the two monopole states are the ones that we can easily control. Yes, sir. This is about the spectrum.
Is there further evidence in explicit?
Is there explicit further evidence? Okay. Yes, there is. People have computed various things using supersymmetric localization. In particular, Waffa and Witten in early paper took n=4 theory, twisted it, and computed the sphere partition function, S4 partition function of this twisted n=4 theory using supersymmetric localization. Okay? Twisted meaning you turn on background R symmetry fields. The reason you do this is you want to, you want there on a curved background, you want there to exist a killing spinner. Okay, now existence of killing spinners is sometimes difficult, doesn't easily happen on curved backgrounds. But if you turn on these R symmetry backgrounds, you can make that happen. Essentially by turning the spinner into a vector. You embed the R symmetry into rotations. Do you understand what I mean? Okay, let me explain this. The reason it's difficult to find killing spinners in curved space is that spinners transform under rotations. Okay, so this, the spinner is on this, is some object in this Wehrbein bundle. Okay, and because the space is curved, the field strength for this Wehrbein bundle is non-trivial, because the field strength for the Wehrbein bundle is essentially the curvature. Okay, and so what you have to do is to find a killing spinner equation. You have to find a killing spinner for some spinner which is d mu psi is equal to 0, where this psi is charged under a gauge field that has non-trivial curvature. Okay, and that's often a difficult thing to do, and sometimes just these things don't exist. Okay, so then supersymmetry is broken. You want supersymmetry to be preserved so you can do calculations. What is the way out? You notice that these spinners, supersymmetries, so the spinners that characterize supersymmetries, are charged under other things than rotations. In our context, what are these other things? It's SO6. So you can take your theory and turn on a background gauge field for SO6. But now, suppose you turn on a background gauge field for SO6 such that the SO6 gauge field is chosen to be equal to the SO4 rotation gauge field. Right, we've got this Beerbine field that lies in SO4. In this SO6, we just choose the same gauge field. Okay, in some sense, we choose it to be equal and opposite. Okay, now our spinner transforms in a bifundamental. It transforms one way in this under this guy and another way under that guy, and different components of the spinner now transform differently. But if you choose it correctly, there will be a component of the spinner that is invariant, one in which you've essentially embedded A is equal to alpha. Do you understand? If you set A equals alpha in the appropriate sense, the rotation of this guy undoes the rotation of that guy. And so this guy now obeys d mu psi is equal to 0, because the gauge field effects cancel out. And it's very easy to satisfy that equation just by setting psi equals a constant. Okay, this procedure is called twisting. To choose the background gauge potentials of global symmetries in such a way to undo the effect of curvature on spinners.
But you're changing the theory.
You are changing the theory. But you see, if the theory was S-duality invariant without these backgrounds, it should be S-duality invariant with these backgrounds, because S-duality does not act in a non-trivial way on SO6. So, if you want to compute something about the theory, well, you've changed it. But if all you want to do is test S-duality, it's fine, right? Right? So you make a prediction. The prediction is that this thing which you can compute should turn out to be basically a, what do you call it, a modular form. Some reason it's a modular form with some weight. I never quite understood that. I would have expected it to be just, anyway, they understand why. So some modular form with, okay, and therefore has good transformation properties with tau under ABCD. So this kind of thing has been done. Okay, this is one of the things that's been done. Another thing that's been done is this. Just like Witten derived Seiberg-Witten theory as a consequence of brain dynamics, S-duality of the n equals 4 theory has been understood as a consequence of S-duality of type 2b theory. Let me tell you about that. Okay. Type 2b theory can be thought of as M theory. Okay. Type 2b theory can be thought of as M theory in some sense on a torus. Should I tell you about it? Okay, let me okay. I will explain this from M theory next time. Right now, just let us remember that type 2b theory is supposed to have S-duality. G goes to 1 over G. So now if you take flat D3 branes, you get n equals 4 Yang-Mills on it. Now just take that configuration, do S-duality on it. Okay. If you do S-duality on it, you get S-duality of. Give me one more minute and let me tell you about this torus. Okay. You remember that we got our n equals 2 theories by M5 brains going all over the place and doing interesting things. You can ask, is there a way to get D3 brains from M5 brains? Okay? At first it sounds ridiculous, right? Because type 2a theory is related to M theory on a circle. Type 2b theory is something else. Okay? Nonetheless, it's possible. The route for doing this goes as follows. You can take the fact that 2a is equal to M theory on S1. Now then just compactify both sides. Okay? Put 2a on S1, on another S1. So 2a on S1 prime is equal to M on S1 times S1 prime. Okay? Now let's take this thing and wrap an M5 brain on S1 plus S1 times S1 prime. Okay, no, I'm just writing S. Otherwise my ones and primes you can't distinguish. S times S prime. Okay? So if we take this M5 brain wrapped on S times S prime, what does that become in 2a theory? 2a theory has only D4 brains and D2 brains. It becomes a D4 brain because M5 brain on the M theory circle is a 4 brain. It becomes 4 brain but wrapped on this S1 circle. Now we T-dualize. Okay, if we T-dualize, this becomes type 2b on S1 prime with the R going to 1 over R. Okay, and on that side we don't do the T-duality, it's just what it is. Okay, but now once we've done the T-duality here, the D4 brain has gone to the D3 brain. Okay, and then we take the size of this S1 prime to infinity. Okay, that is same as taking this S1 to 0 here, and that does something in M theory. What it does, it turns out, is to shrink the overall size of the torus, but leave its shape unchanged. I'm tempted to show this to you, but maybe next time. Okay, so, but to leave its shape unchanged. And one going through this procedure, one sees that the tau parameter of the effective D3 brain theory equals the tau parameter of the torus in M theory. Okay, and now S duality simply becomes the statement that the same torus can be it's just SL2Z of the torus. The same torus is described, tau that differ by SL2Z describe the same torus. Okay, so it's linked to this. There have been many other kinds of checks. Instantons. The stuff involving instantons in n equals 4 has been shown to have this S duality. There are several checks. Usually, almost all with supersymmetric things. But okay. But all this happened after Ashok. It was psychologically extremely important because nobody really believed it. Okay, yeah.